So I see we have a lot of students in the audience, which I think is due to getting extra credit at the end of the semester, but you're in luck because this is actually the greatest topic that you could have fallen into. I think it's one of the neatest missions that I've been a part of and that LASP has been a part of in recent history, and I think you'll be hearing a lot more about magnetic reconnection in coming years. So I'm going to talk a little bit about several different points of discussion that I want to bring up. First and foremost, what the heck is magnetic reconnection? I'm sure most of you have that exact same question. That's why you're here. Next, why do we study it? Why do we care? What is the MMS mission? What do the spacecraft look like and what do they do? And then finally, how does MMS really help us improve our understanding of the physical environment in which we live, in the plasma environment, in our Earth system, and in our solar system? So first I'm going to go back to basics. A lot of you know some of these concepts already, but it's always good to get another refresher. So we're going to talk a lot about magnets, hence the name magnetic reconnection. And so I wanted to talk a little bit about the behavior of what magnets are like, such that we know them. First of all, you're probably familiar with a bar magnet. These are magnetic materials. But you may be less familiar with the concept that there is a huge bar magnet in the center of the Earth, and it actually generates a magnetic field that emanates out from that dynamo in the center of the Earth and goes out into space until it interacts with the magnetic field that also emanates from our sun and eventually collides with the one that comes from the Earth, which I'll talk about in a minute. So we have magnetic fields all around us. We live in these magnetic fields daily. But the place that magnetic fields really matter most is not here in your bar magnet, but it's really where we have plasmas. Okay, so here on Earth, where we're sitting now, we don't have a lot of plasma around. So what is plasma? Well, it's really a fourth state of matter. So everyone's familiar with three states of matter: solid, liquid, gas, right? So when you're at low temperature and or energy, you're really in the solid phase here on the left. Then when you get a little bit higher, your molecules start to move around a little bit. You go into this liquid state of matter. Finally, you go into this gaseous state. But there's actually a fourth state of matter called a plasma, in which atoms actually divide into electrons and protons, and you get this ionized, very hot, ionized sort of gas that we call plasma. There's actually a lot of plasma in the universe, even though there's none where we're sitting in this room. Well, actually, there is some up in these, some of the fluorescent signs that you see, but there's a lot of plasma in the universe, and actually some estimates say that 99% of all the visible matter in the universe is actually plasma, so it does matter. And the key point that I want to get across to you is that plasmas interact very strongly with magnetic fields. Okay, so here's where the magnetic fields come in. So we have magnetic fields out in these plasma environments. They interact very strongly together, and that's what we want to study because it has a lot of effects that we're interested in. So there are a few things that magnets do that we know, and I put that in quotes because at one point we thought we knew a lot of these things. Some of them have turned out to be wrong. But first, what we do know is that magnets have two poles. So you think again of your bar magnet. You have a north and a south pole, and you have your field lines connecting that north to south pole. You don't have any monopoles. There's no north pole disconnected sitting off somewhere by itself. Those don't exist. So magnets have two poles. They also have field lines that do not end. So even though this picture here kind of shows field lines that maybe go off into space where you can't see, they actually don't end. They'll just keep getting further and further away from that magnet and then connecting to the other pole. So they don't just go off somewhere and have an end point unless it's at a pole of a magnet. The other thing that we thought we knew was that field lines don't break. Okay, but really they kind of do. So if you think about two different bar magnets with opposite polarities, you're going to get two oppositely directed magnetic fields. And what happens if you bring those bar magnets towards each other? Well, at a certain point, what you had as two different magnetic field configurations are actually going to merge or break and reconnect, and you eventually would draw a picture that looks like this, where you have some field lines that start on one magnet and emanate from there, go and connect to the pole of the other magnet. So they kind of do reconfigure in certain situations. And then I like to put this one in there because it is an important question, is wait a minute, do field lines even exist? How is the typical way that we observe field lines? Or what's the experiment that you've done where you can actually see the field lines? You've all done this. Right, the iron filings where you sprinkle it around the bar magnet, and all of a sudden you can see that magnetic field configuration jump out. But do those field lines exist until without having those particles in place? And what exactly is a field line? Those are actually still questions that we grapple with even studying these things. So now I want to tell you what magnetic reconnection is. If you go away with one thing from this talk, hopefully it's that you can get across to other people, is that magnetic reconnection is actually an explosion. It's a magnetic explosion. And it affects magnetic fields, but also plasmas in the vicinity of that explosion. So, it doesn't really look like that, but as an analogy, it is truly an explosion, a large amount of energy at a very small point in space. What really happens is that the magnetic field topology changes very suddenly. So you have magnetic field lines that were oriented in one way, configured in one way, and suddenly they're oriented in a different way. What happens in between is the big mystery. Field lines really do break and reconnect, or they seem to break and reconnect. And most importantly, for a lot of processes, is that you convert that magnetic energy. So when those field lines feel tension and they feel pressure, there's magnetic energy within that. And what happens during the reconnection process is you convert that very quickly into kinetic and thermal energy. So you're really taking one type of energy and converting it directly into another. And that's a very powerful thing when that happens in nature. So what happens when field lines break? I said that they can break and they can reform under certain circumstances. So what you really need to have is the right topology. And it looks like this. So you start with oppositely directed magnetic fields, and you move them closer together, kind of like those two bar magnets, but it also works with the Earth and the Sun being two sources of magnetic fields, and it also works with our galaxy and the Sun, and I'll talk about that a little later. But what you have are these two fields that, for whatever reason, get closer and closer together, or they meet and they're going in opposite directions, and then when they feel enough pressure in this direction or enough force in this direction, they can actually meet. All the magic happens right in here, and then they reconnect, and you can see those colors indicating what they were and what they've become now, and then they jet off in opposite directions from that reconnection site, going to the right and to the left in their new configuration. So if you imagine this as a larger picture, you have these two fields, which are now completely different field lines. They have broken, they have reconnected with other field lines. Here's a nice animation that shows that happening continuously. And reconnection can happen continuously, or it can happen in a bursty way, and we don't really know what controls either one of those situations very well yet. But this is, of course, an idealized situation. But you can have this self-sustaining process in which you keep having magnetic field lines flowing in from the top and the bottom here. They will keep reconnecting, and then they will jet out to the right and left, and it can be a conveyor belt of energy transfer. Here in the middle is a current sheet going into the board, and that's important for lots of other things. We're not going to talk too much about current sheets, but they do exist sort of at that magnetic null in the reconnection site. So when we talked about the two bar magnets getting together, maybe you've done that before, you've had two magnets come together. They don't result in an explosion. That doesn't happen in air, on Earth, in any situation that we're familiar with. And that's because reconnection in plasma is special. It's not simply a reconfiguration of field lines. It has a lot of other things associated with it. Mainly that's because magnetic field lines feel a tension when they're in a plasma, or when a plasma generates magnetic field lines, or when magnetic field lines control the plasma. They can also stretch and snap, sort of like rubber bands. So you definitely have to apply energy to get them to stretch, but you can get them to stretch, and they do stretch, they twist, and then they can break and snap back in either direction. Actually, we had a very famous scientist in our field, the only space physicist to ever win a Nobel Prize, Hannes Alfvén, and he hated this analogy. He just hated the fact that rubber bands were used to explain magnetic field lines and magnetic reconnection, but it does kind of make sense. If you look at it in a macroscopic view, it does act a lot like magnetic reconnection, and that snapping back and that energy that's generated. The other thing that's very special in a plasma is that the created field lines are very bent when reconnection happens. So if you remember our picture of reconnection, you had the top and bottom oppositely directed field lines were somewhat parallel, or they were at least more aligned with each other. Remember, they're coming from, say, the Earth and the Sun. They're at a very large distance from those bodies, but the reconnected field lines, or the ones that are created, are very bent. And then plasma gets carried to the left and to the right on those field lines, and they jet outward, and the plasma gets accelerated as well. So that's all stuff that happens when you have reconnection in a plasma. Reconnection in a plasma can also sustain itself, like I said, that conveyor belt sort of motion, and that's very special to the plasma environment. So where does magnetic reconnection happen? And I want to say that it's literally everywhere in the universe, except probably in this room, right? But everywhere that there is plasma, everywhere that you're in a plasma environment, so most of the universe that you probably never think about, but that's where it's happening. So we have it happening on the sun. We have CMEs, coronal mass ejections that you may have heard about, solar flares you may have heard about. So those are actually magnetic field loops that end up getting stretched, they twist, they have reconnection that happens at those loops, and that's how you can launch a huge burst of material off of that CME or off of that flare, and it ends up traveling towards Earth and impacting our magnetosphere. So it's very important for that process. We also see reconnection happening at Earth's magnetic field. So we see it happening here on the day side, the side that's pointed towards the sun. We have reconnection happening here almost all the time. And then we also have reconnection happening back in the Earth's magnetotail. I'll talk more about both of these processes, but the stuff back in the tail is what can cause the aurora that you may see, the northern lights here on Earth. We also have reconnection happening at the very edges of our solar system. So out at the heliopause, we have our Voyagers that have gone through that region now, and we can see that there's material that actually, or we can imagine that there's material that actually gets transported across that heliopause due to these reconnection effects. We see it happen, or we think it happens, in the vicinity of black holes and accretion disks as well. So it's very important for astrophysical concepts. And then we also see it happen in fusion reactors, such as the tokamak designs that we do work with here on Earth. And that's actually an unwanted consequence. They don't want reconnection to happen because it kind of shuts down the system. But it does happen in fusion reactors, and it's potentially a source of a large amount of energy if we can get it to happen under the right conditions and somehow harness that energy. So yes, it happens everywhere. We have all these plasmas, but really, why do we care? Well, what studying reconnection does is it helps us understand the forces that shape our lives here on Earth. You may not know it, but there's actually things that are happening out in space that affect your daily life every day. We call these effects space weather. And the really harmful space weather originates from the sun initially, and from those coronal mass ejections and other explosive events that happen on the sun. What they can do is they can affect a lot of different systems that we rely on here on Earth. So the space weather events can affect, well, space travel, so astronauts that are going to the ISS, satellites that are in orbit, communication satellites, other hardware on critical satellites that we use every day. We see them affect airline transportation, planes will get rerouted from the poles when you have these kinds of events. We see spacecraft failures, anomalies, and then even down to the ground level, we can have disruptions in the power grid, although we haven't seen a huge one at really human concentrated latitudes yet, but nevertheless it will happen eventually. So that's why we say we care. We want to understand how this reconnection really drives these CME events, these flare events, how they end up reconnecting when they get to Earth's magnetosphere, and then again how they propagate down to all these systems. But I also want to add, why do we really care, or why do I really care as a scientist? And it's because I'm curious, and hopefully some of you are as well. So we see these CME events happen. They propagate through interplanetary space. They impact the magnetosphere. You have a geomagnetic storm occur, and you see something like this. Well, if you were flying on the ISS, you would see something like this happen in the form of visible aurora down on the planet below. And this is just incredible. Reconnection happens at every point along the way, from the surface of the sun all the way to when you have these auroras appear in the Earth's ionosphere. So this is really interesting to scientists. And then I also wanted to show a really great flare that was captured from April 2016. This is from NASA's Solar Dynamics Observatory. You can see the filaments, the filamentary structures that are showing up here. You can see them erupt and start to sort of burst away from the sun. This is showing it in different wavelengths. But these are the kinds of really explosive, you can't even imagine how much energy is getting transferred in that moment. And it's just an incredible thing to study. And then the other reason that we really need to know is that eventually we will need to give a weather report to humans that are living on other planets, humans that are living on Mars. This is really not too far in the future for our society. And we don't have some of the protections on Mars that we have here on Earth to protect against space weather events, natural protections such as the magnetic field. And so we really need to give these guys a weather report and be able to predict what's going to happen. So we definitely want to know more about reconnection. And I want to give you this tagline as well to take with you, because this is a good one. If someone asks you, what's magnetic reconnection? You could say, magnetic fields go in, energy comes out. It's sort of that simple. So you have a lot of buildup of magnetic field, and you get a bunch of energy out. It's really an incredible process. But how do we see reconnection happen? It's very hard to see. These are invisible field lines. How do we actually see reconnection? Well, we can try things in the laboratory, but we also have a really perfect natural laboratory. That's one of the greatest things about studying Earth and Earth systems in near-Earth space, is that it's a perfect laboratory that we can access fairly easily these days. So let's just send a few satellites up there and see what happens. And this is how MMS was originally born. So I'm going to talk a little bit in detail about how we look at reconnection, how we measure reconnection. And so in order to do that, we need to first talk about reconnection scales. So what sizes are we looking at? Where are we trying to measure? So reconnection regions happen really in these small boxes. They're very small areas compared to the natural laboratory that you've sent your spacecraft into. These areas are set by motions of charged particles that gyrate around a field line. So here's a magnetic field line, and you have a particle that gyrates around that. That's a natural particle motion. We call it gyromotion. And electrons and ions are both very heavily trapped to that field line, and they both gyrate in different directions and with different radii around that same field line. So we have this frozen in field idea where these particles are really entrained to that field, but that idea breaks down when you start to get to these very small scales. Yes?
You're showing boxes as if this is 2D, but it's obviously 3D, and I really want to know, are we looking at a plane or what's?
Yeah, so this is definitely 2D, and a lot of the reconnection work that we do is still in 2D because 3D is very hard. That's why MMS was really in the configuration that it's in. And I'll go over that a little bit more later, but it's in a 3D tetrahedron. So there's 4 spacecraft that are sort of like the corners of a cube, and you really want that 3D spatial separation to be able to see what's happening in both planes, not just in this cartoon plane that I'm showing here.
But should we imagine a plane?
Yep.
What's on my side and the far side?
So a lot of people just imagine a very long box coming out of the screen and going off into infinity. Yeah. But of course, that's not reality. There's always regions that this happens in, and those are usually, you know, sort of weird shapes. They're definitely not boxes like we're drawing in the cartoon. But really, what sets this area that you want to look into is the motion of those particles around the magnetic field lines. So because ions are heavier and they make larger circles around that field line, we have an ion region, which is this larger box, and an electron region, which is this smaller box embedded within. Now, this is not to scale. The electron region is actually much, much smaller when you compare with the ion region. But we have these two different regions, and so we can say, okay, sometimes we'll be going through maybe the ion diffusion region. Maybe we'll cut across like this through this cartoon picture. And then sometimes, even more rarely, we'll actually go right through the middle, right through that electron diffusion region, and that's really sort of the holy grail of reconnection, because what's happening down on those electron scales is the hardest to get to, and that's what we want to get to. So in these diffusion regions, these boxes that we're drawing here, the plasma actually becomes demagnetized, and it doesn't have to follow the field lines. So it will not necessarily gyrate around this field line, going as it goes, how it bends here and how it bends here. It can go off in different directions, and basically weird things happen. They have weird trajectories. They can get, you know, entrained onto other field lines that they weren't on before, and a lot of strange things happen in those diffusion regions, so they're really interesting.
Are the magnetic field lines truly discrete lines like threads, or is that just a conception where you're just taking a line out of the plane?
Yeah, so it's definitely a conception, and a lot of times if you, again, it's hard to talk about 3D, but if you want to think about 3D, we actually think of bundles of these magnetic field lines, and we call them flux tubes or flux ropes, and we think of them as, you know, three-dimensional ropes or tubes that are kind of coming out of the board and twisting around and getting tangled up with each other, and those can break and reconnect and all of that. But you're right, they're not really threads, and this is all just conceptual, because magnetic field lines really, you know, don't exist except for the plasma that is there to show us those fields.
So when you talk about a field here, are you talking about as a mathematical field?
Yeah, I'm talking about a conceptual field, yes.
Okay, so I'm saying there's a potential for energy at that point.
Yes.
There is nothing there that actually defines that.
That's
So,
right.
So you're saying that that's, say, in this, using a general motion object or image here on your right, then that particle is able to resonate at that particular frequency that's defined by the potential that's there. And that's what really starts it moving.
Yeah, that's right.
It follows, it's just
Exactly.
it's like a hallway, if you will. There's nothing there, but it defines a place for that.
Right, there is not a real thread there in space, but you're right. It
So what
is defined by the plasma.
That particle of the potential at that position.
I'm sorry, what was the question?
How does that particle come to realize that there is a potential at that location?
Sure. So it does feel a force. So there, you know, we don't have a real good answer for necessarily what creates that force, but it does feel a force, and so it does, you know, it is constrained to follow these laws of motion due to that magnetic field.
So are there real photons in that area, or are there virtual photons in that area?
So none of these are. This would be something like a charged particle. So it would be something like an electron or an ion would be in this region.
Yeah, but what informs it?
What informs it?
Yeah.
Well, you can go into a whole lot of theory about, you know, what sets up a magnetic field, and, you know, why particles then have to be entrained or frozen in. There's a, you know, that whole frozen in theorem I talked about. That's a very long discussion that we could have.
How much off the hook?
It's very interesting though. Some people even say, there really aren't any magnetic fields and we should stop thinking about these things as if they are lines in space and as if they really exist as a physical structure, because you can argue that they don't. So the challenge that we face when we're trying to design a mission to look at things that don't exist is never-ending, but really what we're trying to get at is these very detailed spatial scales, and this is really like looking for a needle in a haystack. So we look at ion scales that in real numbers looks like hundreds of kilometers, and this depends where you are in the magnetic field configuration, but it's about hundreds of kilometers. And then the electron scale, that very small box that was drawn in the middle of the region, is about tens of kilometers. So there, right away, you have different scales for ions and electrons. And then the Earth's magnetosphere, if you want to think about that as a whole big picture that we're flying through, is 1 million kilometers or even more. So you're trying to find a region that's happening in tens of kilometer area in 1 million kilometer sized system. It's very, very difficult. So what we need to do is look really, really well. We need to know exactly what we're seeing when we're making these observations. And we really need to look really quickly. So everything is really fast on MMS. We get lots of data every second. Everything takes measurements and samples very, very quickly. Reconnection, you blink and you miss it. We're showing plots that are zooming in on milliseconds of time, and you're seeing things happen. That's how fast it is. And then reconnection truly is a multi-scale process. So again, we're looking at things that affect the Earth's magnetic field, this huge system, but they're happening on these different scales. And that's where the multi-scale comes in. And the whole challenge was headed up by our captain or our principal investigator, Jim Birch from Southwest Research Institute, who's just done an amazing job at leading this whole herd of cats in this direction. So I want to talk about the MMS difference, because this is really what sets it apart from other missions. Obviously, we've had other missions that have flown in the Earth's magnetic field and have made similar measurements. MMS is different for several reasons. First of all, there are 4 identically instrumented spacecraft. I touched on this a little bit, but we have these 4 that are flying in a formation and changing the separation between them over time, such that we're looking at these different scales, these different scale sizes, and we're looking in 3 dimensions. So we can see what's happening, over in that corner of the room, as well as in this corner of the room at the same time. And so we have, altitude information, we have left and right information, all at the same time. That's very important. And then we also have different orbits, which I'll talk about, which we've planned for years of time to cover these different regions in which reconnection occurs most often. And then we have these really fast, detailed measurements. We have to measure magnetic fields, electric fields, plasma waves, and the particles. The particles are important, and you need to measure them over, it turns out, a very wide range of energies, which is difficult. So I would say that if you're going to compare MMS to previous spacecraft, there's been a lot of things that have made these measurements, but you would maybe say that MMS is the mountain lion, like we have here in the foothills and the Rocky Mountains, and everybody else is just your cat, your generic household cat. I mean, you work with what you have, right? So we've done a lot of science with this. We really have. But now we have MMS, and the pace is just on a totally different level, and it's been incredible. So I'll tell you right away what MMS stands for. It's Magnetospheric Multiscale Mission, or Magnetospheric Multiscale, really. But if you Google MMS, it can be a little hard to find information about it. Actually, if you just Google that, usually what you come up with is something like this. And it has nothing to do, obviously, with the NASA mission. So you have to add MMS NASA or MMS Mission in there, and then you get what you're looking for. So the mission was really designed for reconnection. We have instruments, lots of instruments. Some of these acronyms, I don't even know myself. There's just so many instruments on one spacecraft, and then we have 4 of them that were launched in this stacked configuration. We have things like the Fast Plasma Investigation, incredible instrument that can measure these full ion distributions in velocity space. They take measurements every 150 milliseconds, and then full electron distributions every 30 milliseconds. That's just incredibly fast, orders of magnitude from what we've had to work with before. Fields instruments that go up to 1,000 times per second. We have these electric field probes. I'll show a movie of this in a minute, but we have these probes that go 200 feet in the spin plane, so in the direction of the hockey puck spin, and then 30 feet tip to tip in the axial direction. That's the really challenging part, but the really important part for measuring these fields accurately. And this boom system that comes out from the top and the bottom is really amazing, and I have a video of how that works in a few slides. But the other important thing that we need to think about is not just how do we measure all this stuff, but where do we want to be? We need to be at the right place at the right time. Again, we don't know when this stuff is really going to happen, but we can make a good guess. We have these regions that magnetic reconnection commonly happens at. So where the solar wind magnetic field lines, conceptual magnetic field lines, come and meet the Earth's magnetic field lines. You have a lot of reconnection taking place there, especially when this solar wind magnetic field is oriented towards the south, or down in this picture, because then it's oppositely directed to the Earth's magnetic field, which is perfect. And then you also have this little pinched region in the tail that can be created from increased solar wind convection, increased solar wind transients that come from the sun. And that is what triggers tail reconnection, sends a burst of plasma towards the Earth, and you end up with aurora and other things happening. So we had to look at both of these regions. It's a very complicated maneuvering system that we had to go through, and the operations people just did an amazing job with being able to change our orbits and getting to both regions. We're just now coming up on this tail region. We've been over here, and we've completed this season, and we're moving towards the tail in just a few days, actually. So the concept of the mission was really cool. This is just an animation, but it really did happen like this. So they had the 4 spacecraft that were stacked inside that fairing in the top of that rocket there. They sent it into space. It was actually a nighttime launch. And then what happens is you sort of open that enclosure, you open that fairing, and it'll show in a second, you pop off the spacecraft. They kind of just jump out of there one by one, and then you have your 4 hockey pucks sitting in space. Then what you need to do is, of course, there's lots of things that you need to deploy on each of those spacecraft. So it took a long time through our commissioning phase to get each one of those individual spacecraft up and running. You have to move all these booms out. It'll show that really neat axial boom come out in a minute that was a helical solid structure that'll pop out from the top and the bottom. You have lots of instrument doors to open and things to turn on and check out. So commissioning took longer than, I would say longer than you would expect for a near-Earth satellite, but it was necessary because we had just so much going on. So there's that helical structure popping out there to create that axial boom. It needs to be a very rigid structure. That was designed by ATK, by Orbital ATK, and worked really well. And then you can have these very long wire booms because of the spinning motion, and that keeps those rigid in the spin plane. But you have to have something fairly solid to go sort of up and down from the spin plane. So that was the concept. The reality was perfect. It was really flawless. So here's a picture of the actual launch from Cape Canaveral. It launched in the evening hours of March 13th, 2015, so just a little over 2 years ago. And it launched at the exact moment the launch window opened. I don't know if any of you in this room were at that launch, but it was incredible. That really hardly ever happens, but it was like 0 seconds into the launch window, and the thing went off, and it was great. It was fantastic. So just one of the harbingers of the success of the mission. So we have very careful operations that have to be planned for this kind of mission. Like I said, we wanted to get this dayside reconnection region as well as that down tail reconnection region. They're at different distances from the Earth, so you have to literally change the orbit. So we have this phase 1 where we swung our apogee, or our point that's in the orbit that's farthest from Earth. We swung that apogee around so it skimmed what we thought would be the right point to catch the day-side magnetopause. And we did catch the day-side magnetopause much of the time. So we kind of swung through there twice and went around the Earth fully twice and had lots of data and many months of time in which we were just hanging out at that boundary. It was really perfect. That was about 12 or a little more Earth radii away from the Earth. And then what we had to do, or what the operations people had to do, was to figure out all these maneuvers to get this apogee to raise. So they had to constantly do these little boosting maneuvers that got this apogee further and further away from Earth, because now we want to swing through this night side at a larger distance, at a larger position away from Earth. This is going to be around 25 Earth radii, because that's where we think the reconnection is really going to take place in the tail. And so we're at that location now, or we're at that apogee now, at 25 Earth radii, more or less, and we're going to swing right through this tail in the coming months this summer. So it's going to be very exciting to see what happens when we get through that phase. And I just want to say all the fantastic work by ops at LASP and Goddard has been amazing. I know that they've done hundreds of these maneuvers over the past 3 months. And everything, as far as I know, has worked absolutely perfectly. And we got to where we needed to be right on time. So the other cool thing about MMS, if you want some trivia, is that it's actually a world record breaker in 2 accounts now. But the most interesting one, I think, is that it holds the world record for the closest flying spacecraft formation in history and of any multi-spacecraft mission. So this was last year sometime, I believe about a year ago. We got down to 7 kilometers separation. So you can see the tetrahedron here. If this was in 3D, you know, one or two of these would be a little more towards you, and a couple others would be a little more into the board. So it flies in this diamond formation, but these separation distances between the spacecraft got down to 7 kilometers, and that's about 4.5 miles, which seems like a long distance, but when you're talking about making sure spacecraft don't crash into each other in the vastness of space, it's actually really small, and it was a huge achievement. And I think we also have another world record that we've made it to at this point in time, and I think that has to do with the GPS and the furthest altitude spacecraft to use GPS. So some trivia about MMS. And then I also wanted to touch on our really impressive data access that we have. You can go to this site right now. Well, don't do it right now, but after this talk, you can go to this website and you can pull up data from just a couple weeks ago. I mean, you may not know what you're looking at right away, but it's just incredible the work that the LASP data systems have put into this to keep the scientists really, really happy, because it's very hard to get data in a presentable format. You have to get it in the right file format, and then you have to be able to plot it and all of this stuff. And the LASP Science Data Center website, which I encourage you to go poke around on, is just incredible. We use it all the time, and it's one of the best things about it. I mean, we get compliments about it all the time. It's one of the best things about this mission. So you don't just need to get the science, you have to also get it out there somehow. So that kind of leads us into what we do for data selection, which is also a little bit complicated. So we don't download all the data from this entire orbital track. We just physically can't do it with the data rates that we are able to send from the spacecraft to the ground, because all this stuff has to get sent through space and then picked up on the ground and read. We cannot download all the data. So what we do is we identify a time, which we call the fast survey part of the orbit, in which we turn on the instruments a little bit higher so they start going a little bit faster. And then we download that data and look at it. And believe me when I say that this has to get looked at, and this is with a fine-tooth comb, that has to get looked at, and then we select these very, very tiny intervals. This is about 2, maybe 4% of the full orbit that we're actually going to be able to collect burst or high-resolution data. So how do we do all that? Well, it relies on these, what we call SIDLs, scientists in the loop. And these are actual people that have to sit there every day. There's someone for every single day of the mission since commissioning was completed There's been a scientist that has looked at this fast survey data for this interval and decided what little chunks of the really high resolution data we can bring down to the ground to have as high quality science data for the researchers to look at. So there's a lot of pressure. There's been, of course, a lot of debate about what's the best data to bring down and, what's the best way to organize it. So it's been a whole process, but I would say overall it's worked really, really well considering the constraints that we're under. I mean, if you had a spacecraft going around taking this amazing data and you saw that you could only get these little red bits out of this entire orbit, that's a little disappointing. I mean, that's how it was designed, but I would say that these little red bits have been extremely valuable that we've gotten, and that's all due to these scientists in the loop. So if you see a scientist in the loop walking around, they might be wearing one of these shirts, definitely give them a hug. This is how to pick them out of a crowd. We actually created this sort of slogan, keep calm and settle down. It can be a very stressful job, but it's extremely valuable to the whole process. So I'm going to end with a few slides on the science, so what we've come up with our big science results lately. But I want to say that we have a lot of questions yet to answer. Thankfully, we have these hundreds of researchers, grad students, everyone working on this mission. But we really don't yet know what the reconnection region looks like in microscopic detail. We have maybe a few events that we've seen, but we cannot really generalize that to what a reconnection region actually looks like. And then remember how the plasma actually gets demagnetized inside those little diffusion regions. How does that happen exactly? We have some evidence, we have some things to look at, but we don't know. We also need to know what are the conditions under which reconnection starts and stops. It's not necessarily happening everywhere all the time, so there has to be a condition to make it, initiate. And then we need to know the rate at which it happens. It can happen really fast, it can happen a little bit slower. What determines that rate? And then how do we accelerate these particles within that reconnection region? So this is another big thing is, how do you get that magnetic energy into particle energy, which is, one of the big unknowns of the field. So we do have some impressive results already. I want to talk first about our big result. This was actually the hit. This was the reconnection region, or one of them. We now probably have many other candidates, but this was the most publicized one, where we went right through one of these little tiny reconnection regions. This was on October 16th, 2015. We think we crossed the X line directly. We have evidence that we were at least near the electron diffusion region, if not in the electron diffusion region. This was on one of those day-side reconnection points, so the part that you're getting the solar wind directly connecting to the Earth's magnetic field. And this was a paper published in Science. We had many, many people at LASP and CU involved with this. It was a huge effort by a lot of different people. And really what you're probably looking at here, or what you're thinking, is these are just squiggly lines, which is true. This is what most of MMS science is squiggly lines. It's very hard to get people interested in squiggly lines. But these squiggly lines are extremely impressive, actually, so take my word for it. There's a big jet reversal that you can see. So in the cartoon, you're looking at these reconnected field lines. Before we were showing them going to the left and right. In this cartoon, they go to the top and bottom, but it's those same things, those really bent field lines that have just been reconnected. They're shooting up, they're shooting down, and they're carrying a bunch of plasma with them. You see really, really strong currents right in that region as well. So this is indicative of lots of dissipation. You see heating of particles, and parallel electric fields, and lots of very interesting things in that region. This cartoon here isn't really the path of the spacecraft, so the spacecraft is not maneuverable. Okay, we're not driving it like a little car through this region. But what we tend to do is draw our magnetic field topology and then pretend that this entire frame is actually still while the spacecraft is moving, where more likely your spacecraft is really sitting somewhere, essentially, and that entire magnetic field topology is flapping back and forth over your spacecraft. So it's a nominal path that the topology makes in reference to the spacecraft. But it does kind of show you, and really nicely, that we cross through these jets, and then we cross right through that little diffusion region, or very near to it, and then back through a jet and into the ambient magnetosphere. So what did we see in more detail? This is actually a simulation of what the magnetic field topology looked like at the time, and this actually changes in time. It's a little video that you can watch and attached to the science paper. But what we really see are these, when we're in that dissipation region or near it, we see these crescent shapes. You see those little half moons that show up in the electron distributions. Those are very indicative of reconnection. Those kind of show that these jets are going up and down away from that reconnection region. You also see acceleration, so you see that there's more red, and these things are becoming more intense when you're in those jet regions and those exhaust regions. So those are like hallmarks of reconnection, and it was incredible to find these. These have been shown in simulations, and then we actually see them in data, and it's just amazing. So it's this event in particular was everything that we had hoped for, and really more, and it will be studied for years to come. I also want to highlight another first that we caught from a first author here at LASP, Stefan Eriksson. And you can see here in this, again, big plot of panels of squiggly lines, but this is showing oscillations in a lot of different plasma parameters and in the particle parameter and in the field parameters. And you're seeing these squiggly lines because you're going through a certain region, which we associate on the boundary with Kelvin-Helmholtz waves. And these are also reconnection jets, so you can see little dashed lines here that correspond to current sheets that are shown more clearly in other sets of squiggly lines. But these current sheets are places where reconnection is occurring, and it's in the midst, it's embedded in this whole region of waves or flapping up and down. And you can look at the schematic here. These are these wave-like structures that we see on the boundary of the magnetopause. This is not really at the point directed right towards the sun, but it's on the flanks. So it's sort of on the dawn and dusk, or the morning and afternoon side of the Earth, not right at that front subsolar point. But we actually did find all this evidence of reconnection happening on those Kelvin-Helmholtz waves, which is really interesting because we know that these Kelvin-Helmholtz waves happen very often on the flanks of the magnetopause, and this was really the first time that we had this great evidence for reconnection happening there. This means that material can be transported in from the solar wind through these interactions. So it's very significant, and I think this is one of the bigger results that we've had out of the mission so far. You may notice that those Kelvin-Helmholtz waves look familiar, and so this is also something I think is really, really cool, is that those same waves occur in Earth's atmosphere, in cloud systems, and that's basically due to this exact same instability, dealing with shear velocities of two different fluids in relation to each other. And so you can say, if you ever see these things happening in Earth's atmosphere, you can say, hey, that happens on the magnetopause, and MMS saw magnetic reconnection there. And your friends will just look at you. Okay, so I would like to end saying that MMS has been a complete success so far. I don't think we've even begun to get into all the data that we have from this amazing mission. We have that success due primarily to the work of this incredible group. We have engineers, we have operations and data teams, we have scientists, we have leaders, and it's really everyone working together that's made this such a success. And I want to really say that every time you look at a system, such as Earth's magnetosphere, on finer and finer detail, so you look at more and more detailed measurements, smaller and smaller scales, it makes less and less sense. But it's one of the things that drives us to do the science that we do. So I hope that you have had a little inspiration from this talk today. Thank you. Any questions?
How long is MMS slated to run?
Oh, that's a good question. So we have this next phase 2B, which we're just starting, and it will carry us through the summer. And then we're hoping to get extended funding, because we've been so successful, to go through a phase 3, which will be, I think, a better part of a year, which will actually start skimming that magnetopause and the flanks where we saw those Kelvin-Helmholtz waves. And so that's sort of an additional bonus. We're just now getting into the second of our primary phases, and so we're kind of completing our primary mission now. Yeah.
How long do you have fuel for? And, you know, on the average, depending on what your orbits are.
Yeah, that's a good question. So, you know, we have fuel for years depending on how we use it. So, you know, there's
You get a lot of extensions then.
yes, we can get a lot of extensions, but there's constantly evolving discussions where the science team talks about what the trade-offs are for making these maneuvers now and using up fuel versus being able to extend the mission to longer times. Yes. Did you have a question? Yeah.
So I always thought that the auroras were caused by the solar wind just hitting our magnetosphere just on this side.
Right.
Are they actually, but you're saying they're actually caused by when they loop around and reconnection happens and they're hitting like the other side?
That's right. So that reconnection that happens in the tail of the magnetosphere, or the night side, and then shoots back towards the Earth and sort of in the sun direction, that's what causes the aurora. So there's really no you know, direct relationship between what's hitting on the sun side and then what you see in the aurora on the night side, but it is related because you can transfer energy from the solar wind to the magnetosphere, and then when you build up energy, you can feel it in the tail, and then you can have a reconnection event occur, and you can kick off these northern lights.
So it only happens when the reconnection occurs?
Yes.
And it shoots it back towards
Yes, but we have on average, you know, a substorm every day or so. I mean, you have at least one a day typically, so it does happen very often. Yeah. Yes.
Are particles from the sun carried all the way to Earth on these magnetic vortexes then?
Yeah, so you can have a lot of different things happen on the sun as far as you know, particle acceleration between the sun and the Earth, and you can also have those magnetic fields sort of changing a little bit as they go from the sun to the Earth. For example, you can have two different plasma blobs run into each other when they're in transit, but those particles do end up impacting the magnetosphere directly, yes, but not the Earth directly. Yes.
So 2 questions. One, if you can, I mean, I guess the first question would be, can you do this in a laboratory? I mean, what's the simplest or most interesting kind of laboratory scale reconnection thing, and what does that look like? And then I'm still trying to get my head around kind of the 3D. You know, if you took this big area that's going to hold these spiraling electrons and ions, what's the density? How many particles are there? Do the particles ever hit each other? Because I imagine they're kind of going, you know, I mean,
Yeah. So
how
normally,
much energy is there?
Right.
In that, if you were in the middle of that reconnection, is it a huge amount of energy, or is it a?
oh yeah. So let me go backwards. So it's a huge amount of energy that happens in that region. I mean, it's an enormous amount on scales, you know, that we don't see on Earth, that we can't reproduce on Earth. First of all, as far as, you know, how to create that in the lab, people are working on it. You know, things have been accomplished, but we're of course not going to be able to see anything like we can observe with MMS. That's why these spacecraft are so important, is because we can go to these places where this stuff happens naturally, you know, and get all these measurements. We can't really set up something that scale here on Earth. And in terms of you know, being able to think of these in 3D, what we really need is to get more computer power into these simulations, so that we don't have to just look at a 2D slice of all this stuff happening, but we can watch it happen in 3D. But that just requires a lot more CPUs, and you know, people are doing things like that. Yes. Yeah.
In terms of density, any?
Oh, right. So we think of these systems really as being collisionless. This is extremely very, you know, low density plasmas. These things don't actually collide. So the way that they interact with each other is through these fields and in collisionless ways. You can study collisional effects, but in general, in how we idealize this, and for the most part, it's very collisionless. Yeah.
Do
Do you have a measurement of what the vacuum is out there? Is it like 10 to the minus 12th torr, 10 to the minus 14th, 15th, something like that?
So it's going to be lower than your cryo pump can do. So whatever, 10 to the minus.
And I'm assuming that the
9 or
twisting of
11.
the field lines and all that is dependent basically on what the plasma is doing, because the plasma is focusing it, and the movement of the ions is what allows things to twist or whatever. Okay.
Yeah. Yep. Yeah, that's a good way to think of it, as these field lines are actually kind of focusing the path of these particles. Yeah.
So what's the end of life of this mission? It's up there. What are you going to do with it when you're done with it?
Well, I mean, if the instruments are still working, and there's always degradation in space, things break down over time, but if the instruments are working, we'll get them out to where they're not going to hit each other. So we'll get them out to large enough distances where different little gravity effects won't bring them into, probably won't crash them together, and we can let them go as long as they last, and as long as we can keep communicating with them and get data back. No.
And they'll have power for. So there's solar panels enough for the instrument.
Yeah. We'll keep using them as long as we can possibly use them, because these are little sensors out in space, and very, very good sensors. Okay. In the back, yeah.
So you were kind of mentioning, I think, right, about how you think that this could potentially eventually be used if we were able to figure out how to as a very significant power source. Was that what you were saying at the very beginning, or did that just mean?
Oh, sure. That's on a lot of people's minds, is how to harness something like the energy that you get out of magnetic reconnection.
So what does that conceptually look like? Like how? I know obviously if you know how to do that, you'd be extremely wealthy. But what sort of I don't know. I guess just conceptually, what sort of thing would capture that?
Right. So the problem really is that you have to use a lot of energy to create these very strong magnetic fields. Whereas if you're, out in the Earth's generated magnetic field or out in the sun's generated magnetic field, those are all free. Those are coming from different processes. You're not using any energy. But if we wanted to do that in a laboratory or in a controlled environment, you have to spend a lot of energy to create these very strong tokamak magnetic fields. But then the idea would be that you could impart that magnetic energy into thermal energy, and then by all of your standard methods, you could harness that somehow. The equation doesn't really work out yet, but people are extremely interested in trying. Did you have a question?
This sounds like a corrosive environment to put the toys in. Are they going to have is it going to shorten their life?
Well, it's actually not too corrosive. It's nothing like the Van Allen probes, for example, that are in the Earth's radiation belts right now.
Okay.
That is a very dangerous and a very bad environment for a spacecraft, and they're still working. They're still doing remarkably well. But anytime you're out in space, you're going to get that radiation. So there's the possibility of getting a single event upset, or actually having radiation damage. We have had collisions, probable collisions already, with very small micro debris.
Okay.
Yeah, so it's a dangerous place.
We also power off the instruments. As we come close to the Earth, we have to power off the instruments so that they don't get overloaded, because they're so sensitive. So they're powered up when they're in the area where we're taking measurements, and we power them down.
So that's a good point. When we get really close to the Earth and into the radiation belts and into the really high, more dense environment, then we actually do turn off a lot of the instruments so that they don't feel those effects. Yeah. I'm going to go right to the back.
So basically, I understand that we use the tetrahedron arrangement just to get the 3D mapping. But individual MMS satellites, all they're doing is just measuring the magnetic field intensity. They're basically magnetic.
They're measuring lots of things, yeah, including magnetic field strength, yes.
Are you looking at the gyro motion of magnetospheric? Is there any specific particle that you're looking at, or just?
Yeah, so we're looking at, we're looking at the electrons, we're looking at the protons. There's also heavier ions that we can measure, and we can measure them on the order of a gyro phase very easily. So we can kind of, see them when they're going this way around the magnetic field, and then when they're completing their orbit around the other side of that magnetic field, we can measure that entire motion, which is really one of the cool things about this. So we look at all of that because all of that's involved in the reconnection process.
Is that like 99% ionized hydrogen, basically? Or?
It depends on what environment you're in, and if when we're going into the tail, we're going to be seeing different compositions than when we're out on the dayside magnetosphere. But yeah, it's a lot of electrons, and it's a lot of protons, and it's some ions. Yeah.
So is your flight configuration on the scale of gyro radius?
The flight configuration.
Yeah, the distance between these guys, is that about what a particle would be doing if it was on a field line?
Right. So we do change that separation from 10 kilometers up to over 100 kilometers, and so we do kind of go through a large range. So every energy will have a different gyro radius. So we do kind of sweep through a large range of our energies, and we can see those gyro radius effects. At the very high energy particles, we don't see the gyro radius. Yeah, they're too large, so everything looks the same on all 4 spacecraft and from every direction, not every direction, but from the entire gyro phase, we can't tell the difference because everything's too big. And blue shirt.
You said the plasma demagnetizes. Has that helped try to figure that out?
Yeah, so that's one of the reasons we need to look so quickly at these things, is we need to see them when they're in that region and they're demagnetized. One of the problems with looking at data like this is that there is so much of it, and every reconnection region is different. So you've seen one reconnection region, you've seen one reconnection region. You cannot generalize to them all. So then you look from one to the next and you think, okay, I know exactly what's going on. Wait, I don't know anything about what's going on. So I think we still have work to do on figuring out what exactly happens in those demagnetized regions. Yeah. Yes.
So along those lines, what's the most surprising result, or what's the biggest surprise with the data shown?
Yeah, so I think one of the biggest surprises is that we have very high energy electrons being created out really far away from the Earth at these, certainly at the dayside magnetopause. We kind of expect to see it in the tail, and we've measured it before in the tail, but out there on that side that points toward the sun, we see things go up to very high energies, and we're not exactly sure why. We didn't expect to see that, and it's a little bit of a mystery, but we definitely do observe it.
How high?
Hundreds of keV in terms of electron energies, and that's a little bit surprising because you think of that as a ring current energy or even approaching a radiation belt energy, and those things are all confined in the stronger magnetic fields closer to Earth. But when you get really far away from Earth, there's other things that can happen, and we think we have guesses as to why those get accelerated. But it was an interesting result. We also see very, very strong parallel electric fields at these reconnection regions. So those are electric fields that are pointed along the magnetic field, and that was another very surprising result. They're kind of stronger than I thought, than a lot of people thought, and so why are they so intense, and what's creating them, what's setting them up? That's an interesting problem. Yes?
So the example you gave for reconnection was bringing 2 bar magnets close together. Does that mean that reconnection only happens when the sun's magnetic field is aligned opposite to the Earth's, and does that ever not happen?
Yeah, so that's a good point. It does happen almost always when you have the sun's magnetic field pointed opposite to Earth. So when you have that southward pointing sun magnetic field on the day side, or when you're kind of looking from the Earth, that magnetic field is going northward. And so when your solar magnetic field that's coming towards that is southward, you will have lots of reconnection. You will have reconnection happening almost continuously. When it starts to move off of that southward orientation, you can still have reconnection. So you can, have some of these other types of reconnection happening that have to do with, the exact orientation. So maybe it's not exactly southward, but it's a little bit off, in either direction in 3D space. But you can also have reconnection happening here. So where those field lines from the sun drape over the Earth's magnetic field, because there you can have oppositely directed magnetic field lines, even if the solar wind magnetic field is straight northward. So you could.
It only happens when the two field lines are directed oppositely?
I would say that there is component reconnection that can happen in other situations, but that, yes, in general, you have to have some sort of component that's oppositely directed, yes. Yeah. Yes.
Have you observed any effects related to, like, the Earth's poles shifting? Some of the experiments that you've got going on?
So, we can't see that so far away from the Earth. It's very hard to see that effect propagated out to these distances, say at the magnetopause where the solar wind starts to hit Earth's magnetosphere. But we do work with the geomagnetic field. We do care about what that geomagnetic field structure looks like closer to Earth as well, and we do see that north magnetic pole is moving, and it's suddenly moving very quickly. So it's interesting to see what will happen. For a while it was meandering around a point, and now it's kind of just moving south. We can't predict what will happen.
Over a time period of weeks or days?
No, over a time period of years, many years. Yeah. But it's still significant. If you plot out, many decades, you will still see it kind of hanging around, and then all of a sudden that North Pole is moving south from the position it was at. Yeah. Yes.
Yeah, just going off from that. So, because I've heard that the fields, the north and south pole will flip completely at some point in the future.
Sure, they have before.
Is that kind of what's happening there as it travels? Is it essentially making that flip, or is it going to be a complete reversal instantaneously?
Yeah, it's possible. We don't really know. We definitely monitor it. And what we can see from geological history is that those poles have flipped, but we don't have the data resolution to see how quickly they flipped. So we know in the span of thousands of years, that they did flip, and then, the north to south did happen, that transition happened. But what the rate was, we really don't have much of an idea.
Yeah,
So.
It'd be interesting to see how that orientation changes with respect to how the sun's magnetic fields hit it as well.
Exactly. It will have a lot of impacts on space weather, on how these solar magnetic fields affect our Earth. Yeah. Oh, yeah. Definitely. Yes.
So we're approaching solar minimum here pretty soon. So the linear cycle, what will that do to it?
Yeah, so, we kind of went through the solar maximum a few years ago. It was an extremely wimpy solar maximum. It was not at all what we expected. There were very few solar transient events that came towards us. There were very few, solar energetic particle events, so large clouds of protons that come towards us at very high energies, and we don't really know why. The minimum could be about the same as the maximum. It could be the deepest minimum we've ever had. We really don't know. And the nice thing about reconnection is that it doesn't really matter if we have one of these huge CMEs. It would be interesting to see what happens when we have a large event, a huge shock that just impacts the magnetosphere, but we don't need to have one. This reconnection process happens all the time, just as a natural consequence of how the fields are usually directed, and they flip around from the sun all the time, so we just kind of constantly have some sort of reconnection happening. Yeah.
Is the sun and the earth aligned now, or are they opposite at the moment?
Aligned.
Fields.
Oh, at the moment, I would have to look at solar wind data.
Yeah.
So they can change on timescales of down to minutes, which is what we measure them at right now.
But the overall magnetic field of the sun, though, is either same as the Earth, or same direction as the Earth, or opposite the Earth for its whole solar cycle and then it switches.
Oh, I see what you mean. Just the general polarity.
Yeah, I'm not sure which way it is.
Yeah, I'm not sure. I'm not sure either about that.
Minimum, so it's kind of neutral.
Yeah, neutral. But you know, the exact way that the field is oriented when it actually comes to our Earth is, you know, changes all the time. Yeah, it just kind of flaps back and forth, and it's very dynamic.
So is that right? So if I have a coronal loop, I'm carrying a pretty intense field with me, and if I do a reconnection and it goes out, I'm carrying essentially my own local magnetic orientation with me, aren't I?
Yes. Yes.
And how that interacts with the Earth's
So
fixed dimension, or relatively fixed, will probably say something about.
yeah, so you know, we say that IMF, or the interplanetary magnetic field, we say that orientation gets fixed at the solar corona. So there's things that happen in the sun's atmosphere, sun's surface, and the sun's atmosphere, but then kind of once it leaves that solar corona, that's where it gets fixed, and that's the direction it will be when it finally comes and propagates towards Earth. But if you look at some of these you know, diagrams of what the solar magnetic field looks like, you know, here's an example right there. You know, you have all these different loops. You have a big sort of rat's nest of magnetic field loops. And so what's directed at Earth at any one time, and you know, how that IMF gets set is changing.
That's pretty much determined by the blob of plasma and how it's moving and interacting and actually kind of holding the magnetic, or focusing the magnetic field lines locally, right?
Right. And that has to do with, you know, how those coronal holes are formed and what, you know, configuration they're in before these things get launched from the sun. And yeah, a lot of stuff going on. Yes.
So it sounds like there's lots of people working on this in different levels. What's your role, or kind of how do you work with the data? Are there particular instruments or aspects of it? What's a day-to-day kind of?
Sure. So I work with one of the instrument teams. I work on the PHEEPS instrument, which measures very high energy electrons, which is why I know about the unexpected high energy electrons at the Earth's magnetopause. And so I kind of, you know, I do everything from data processing, so data that's coming directly off the spacecraft, getting it into a good format for scientists to use. I do instrument maintenance and instrument calibration. I then actually analyze the data and write code to make plots and hopefully publish papers with it. And you know, I also do things like CITL activity. So I do scientists in the loop, where I sit there and decide which little tiny segments to bring down at the highest resolution. So lots of different activities. Yes.
Who designed and built the spacecraft?
Oh, that's a good question. So there are many different well, you saw all those instruments that are involved, and there were even international partners, and then also institutions from all across the US that were involved in making those different instruments. But then the spacecraft themselves were designed at NASA Goddard. So Goddard Space Flight Center designed the bus and the spacecraft that ended up being the final full MMS. But then the instruments were contributions from lots of different institutions.
Were some of those instruments designed here?
Yeah, so some of the double probe instruments, some of the components of those instruments were designed here at LASP, and yeah, that was the main contribution in terms of instruments, and some of the boards for the field suite were designed here. Yeah.
Batteries for each satellite was built in Longmont.
That's yeah.
I worked.
Oh, okay, nice.
So I know.
Yeah, and then then there's orbital involvement, and there's lots of different people that played a role. It was a big team. Yeah. Okay, thanks everyone for coming.